So in managing the RWND value, we can sometimes come to a situation where host B's RWND value goes down to 0, and now in our bidirectional communication, host B doesn't have anything to send to A. So basically, in order to maintain the connection, host A sends a 1-byte message to host B, so it knows host B is out there. The messages are acknowledged by host B. Then eventually, host B will have an RWND value that's non-zero, and then host A can then start sending data to host B again. The next thing we're going to talk about is the concept of connection management. We talked a little bit when we looked at the TCP header about some different flags that are used for setting up and tearing down a connection. So we're going to talk a little bit about how that works. So before in TCP, before the sender and receiver can exchange data, they basically establish a connection. And this allows them to not only make sure the other person is there and they can receive data, it sets up some of the connection parameters that allow us to have a reliable connection. And you can see from the code point of view, when you do the socket, client socket equals new socket command, and you set up the different parameters, that's basically what you're doing, is you're setting up the initial parameters that are going to be sent back and forth. And at the other end, you are accepting those connection parameters. So let's take a look at what some of those parameters are. So there's a connection state of establish. We're not sending data, we're establishing a connection. We're setting up connection variables. So I'm setting up sequence numbers and the received buffer size. So that's known at the server and at the client. And then we are ready to have our three-way handshake. So this is basically set up to ensure that a connection can be established. The reason we have a three-way handshake instead of a two-way handshake, because we don't want to be in the situation where we're not absolutely sure that both sides are alive and ready to accept data. So you have the client over here that is going to initiate a connection with the server. So it chooses its initial sequence number with the value of X, and it sends a TCP SYN for synchronized message. So basically, this number is one of the flags in the header, and that is used when we're trying to set up an initial connection. So the SYN bit is set to 1. Sequence number is X. The server is listening on a particular port. It receives that message with the SYN bit set to 1. It chooses its initial sequence number Y, and it sends a SYN acknowledge message back, acknowledging the SYN bit that it received. That's ready to set up a connection with the client. So its SYN bit is set to 1, sequence number is set to Y, which is its initial sequence number. Its ACK bit is set to 1, and its acknowledgement number is X plus 1, continuing that next sequence number expected value. At the client end, it receives the SYN ACK, indicating that the server is alive. It can send the ACK for the SYN ACK. It may also start sending data at this point. And then by doing this three-way handshake, we establish at the client end that the server is alive, and at this end, we establish that the client is alive, which is the purpose of this, the third part of the three-way handshake. So this last part, we acknowledge to the server that we received this acknowledgement, and we give it the acknowledged number so we know we didn't lose any data, and now we can also start sending data. In closing a connection, the client and server each close their side of the connection. They do this by sending a TCP segment with the FIN bit for finish set to 1, and it responds to a received FIN with an acknowledgement. On the receiving FIN, the acknowledgement can be combined with its own FIN. And this way, simultaneous FIN exchanges can be handled. And here we have the specific details of how a connection is closed. So the client reaches a point where it wants to close the socket. So it's no longer going to send once it closes the socket, but it can receive data. Sets the FIN bit to 1, the sequence number. The server acknowledges that, sends it to the server. Then the client waits. So basically, the server first acknowledges that the client wants to close. Then the client can still send data. When it's done sending data, then the server says, "Okay, now I'm done." And then the client acknowledges to the server that I get the message you're done. The server closes the connection at this end, and just in case this FIN bit gets gets lost, so this connection doesn't just hang out there forever, there is a timer that waits for 2 times the maximum segment lifetime. At this point, after waiting that long, it says, "Oh, I'm sure the server will probably close the connection. I just didn't get the acknowledgement. Just so I don't leave this connection open for the future, I'm going to close it." And so close the connection either when receiving the acknowledgement and receiving the FIN bit from the server, or when the timeout value is reached. Okay, next we're going to talk about the specifics of TCP connection control. Like I mentioned in the past, we covered principles of connection control in 475. I'm going to assume that you're familiar with this in 475 or any previous classes, so I'm not going to go over principles of congestion control. However, the slides in the additional material has that information if you want to go over that on your own for your own review. So let's take a look at how TCP does connection control. The TCP mechanism for congestion control addresses the situation using a process called additive increase and multiplicative decrease. So basically, that this is a very conservative approach to dealing with congestion on the network, where we back off very quickly if we feel that we're starting to have some data losses. So the approach is basically the sender increases its transmission rate, which is basically our congestion window size, probing for usable bandwidth until the loss occurs. The assumption here is, based on the network traffic, the bigger we make the window size, and we don't have any losses, that means we have plenty of bandwidth, and we keep on increasing it until we reach the point where we have some data loss. So the assumption is, on the greater network that we're on, we're hitting a point where there's some sort of switch port or something somewhere where a buffer is getting overflowed and packets are getting dropped because we are sending data at too fast of a rate relative to the other users on the network. So that's why we back off. So like I said, we increase the transmission rate until a loss occurs. So we call that increase an additive increase. We increase the congestion window by one maximum segment size for every round trip time until a loss is detected. So every time we receive an acknowledgement back, we increase the congestion window. Once we have a loss, we cut the congestion window in half. So it kind of gives us this sawtooth drawing where this is time and this is the congestion window size. So we increase that up to some point, we have a loss, we decrease it in half, then we keep on increasing until we get another loss, and so on and so forth. So let's take a look at some of the details of how we set this up. So here we have an example of, oops, sorry about that. This mouse is a little bit flaky. Here we have an example. We have our congestion window. It includes the first packet that's been sent but not yet acknowledged. And we've obviously sent fewer packets than we can. We're still using this window. So we have a few more that we can send. Our sender limits its transmission so that the congestion window is based on bytes sent versus bytes acknowledged. So if you add up the last byte sent minus the last byte acknowledged, that has to be less than or equal to the congestion window size. So this is going to fluctuate, like I said, based on any losses that we receive. So basically, the rate that TCP is going to send is going to be driven by the congestion window and the round trip time for acknowledgements. So the rate is going to be approximately, we're going to be able to send the number of bytes in the congestion window divided by the round trip time. So that's going to be our bytes per second data rate. So basically there are three mechanisms that TCP congestion control uses to control the congestion window. We're going to talk about them each individually. The first one is called slow start. The second one is called congestion avoidance. And the third one is called fast recovery. Let's start off by looking at slow start. So when the connection begins, we increase our rate exponentially until the first loss occurs. So we initially start with our congestion window at one maximum segment size. Then we double that every round trip time. And this is done by incrementing the congestion window for every acknowledgement received. So what happens here is the initial rate is low, but it ramps up exponentially. So we start off with one segment, we get our first acknowledgement, then we double that to 2, and then we increase that to 4, etc., etc. If there is some sort of loss event, we set the congestion window back down to 1, and we set our SH threshold to half the value of the congestion window at the time the loss occurs. If there is no more losses, so the SS segment size threshold is basically the highest that we're going to go as far as the size of our congestion window. If no more losses occur, then the congestion window value will double until we reach that SS value is reached, and then TCP transitions to what's called congestion avoidance mode. In congestion avoidance mode, it's a little bit slower than our slow start. We increase the size of the congestion window by a more conservative approach, basically one maximum segment size every round trip time. And this is usually accomplished by increasing the congestion window by maximum segment size bytes whenever an acknowledgement occurs. So, let's say look at an example. If we have a maximum segment size of 1460 bytes, and our congestion window is 10 times that, of 14,600 bytes, then we're going to send 10 segments within a round trip time. Therefore, each acknowledgement increases the congestion window by 1/10 the maximum segment size, as opposed to before we were increasing it by 1 maximum segment size. Therefore, it just increases by 1 after acknowledgements once the 10 segments have been received. So in this case, we increase the congestion window at a slower rate. If there is a loss indicated by a timeout while doing congestion avoidance, then we transition back to slow start. If there's a loss indicated by 3 duplicate acknowledgements, then TCP transitions to what is called fast recovery. And this is basically a newer feature for TCP. So, in TCP fast recovery, what we do is we look for the case where we have 3 duplicate acknowledgements. So what this means that we basically lost a packet, but the duplicate acknowledgements tell us that the network is still capable of delivering some segments. We then set our segment size threshold to be half of the congestion window, and we set the congestion window to be the segment size threshold plus 3, and then we grow linearly for each duplicate acknowledgement received. Once a new acknowledgement is received, then the TCP transitions back to congestion control. So basically at this point we're pretty satisfied that the network is in good shape and we're not expecting any more any additional data loss. So here we have a summary of how all those 3 mechanisms in TCP congestion control work. So first, let's start off by looking at the slow start mechanism. We start off with our initial conditions, in this case a command window, congestion window set to 1 maximum segment size, and our segment size threshold at 64 kbytes. And we start off with our duplicate acknowledgement count to 0. Just looking at the good condition, we keep on getting new acknowledgements. We basically increase our congestion window size to congestion window plus the maximum segment size every time we we receive an acknowledgement. So when things are going good, this is what's happening. If we get a duplicate acknowledgement, we keep track of that, and we don't do anything unless that count is equal to 3. If we have a timeout, then we basically drop down. We bring our set our threshold to half the congestion window size. We set our congestion window size to 1 maximum segment size, and we start again. We keep on going, and if we reach the point where our congestion window equals the threshold, then we go into congestion avoidance mode. If we reach the point where we end up with 3 duplicate acknowledgements, we go to fast recovery. So let's assume we do our slow start, we have our timeout, then after that we keep on increasing until we hit the point where the congestion window is greater than or equal to our segment size threshold. So then we go to congestion avoidance. Let's say things are going well. We get new acknowledgements. This time we increase the congestion window by a slower rate than we did here for slow start. Things are going well. Then maybe we get some duplicate acknowledgements. Once that count is equal to 3, we have to drop down to fast recovery. If things aren't going well, and instead of duplicate acknowledgements we just got getting timeouts, then we're going to migrate over to slow start. If we go into fast recovery, for every continual duplicate acknowledgement, we're going to just increase the congestion window. If we get a new acknowledgement, then we will pop out of fast recovery and go to congestion avoidance. And if we get a timeout where we're not getting any acknowledgements at all, we're going to migrate to back to slow start. So basically, by going through these 3 mechanisms, we have a way to control congestion, and we end up with that sawtooth timeline that we saw previously. So this concludes our review of the transport layer. Now we're going to migrate to our next set of lectures for the week, and just like this one, we're just going to, since it's a review, we're just going to cover the key points so we can move on to some higher level implementation discussions.